As we are learning different derivatives, we're going to continue to add these different derivative rules, so no longer the definition, the derivative rules to our tool belt. Today we're going to add in derivative of trig functions. We can find these derivatives. Now I've already written the derivative rules for you. I'm going to read them to you and I'll try to help you memorize them. The derivative of sine is cosine. The derivative of cosine is negative sine. Cool. The reason I have these on top of each other is because there is a trick to memorizing them, and we call it the Santa Claus negative Santa Claus rule. Here's how it works. Let's write that down. Santa Claus, and then negative Santa Claus. The reason that this is helpful is because if you take the derivative of sine, what is it? Cosine. And then if you take derivative of cosine, what is it? Negative. And if you take the derivative of negative sine, it is negative cosine. If you take the derivative of negative cosine, it is positive sine. So you will go like in this order. Sorry, what? The derivative of sine is cosine. The derivative of cosine, negative sine. The derivative of negative sine, negative cosine. The derivative of negative cosine, positive sine.
So all that is there's 4 formulas including the first 2.
Correct. It's just a visual way to remember these two rules.
Hello. These 2 formulas and then 2 hidden ones.
So wait, so the derivative of negative sine is cosine, right?
Negative cosine. Because it's on the negative Santa Claus one.
Derivative of negative cosine.
Positive sine. Okay, watch it again. Watch the little arrow go around. The derivative of sine is cosine. The derivative of cosine, negative sine. The derivative of negative sine, negative cosine. The derivative of negative cosine, sine. They repeat in this order. The derivative of sine is cosine. The derivative of cosine is negative sine. The derivative of negative sine, negative cosine. Derivative of negative cosine, positive sine.
So it's kind of like a z back to the beginning?
However it looks to you, yes, that's exactly what it is. Make it make sense to yourself. Okay? It's just helpful to memorize it. Santa Claus, negative Santa Claus. The second derivative rules for trig functions. The derivative of tangent is secant squared. The derivative of secant is secant tangent. Here's how you can remember this. Make a nice little cute little triangle. I'm gonna make mine cuter. That's better. At the top you write tangent. And on both sides you write secant. This is how you remember the derivatives for tangent. This triangle with secant and tangent. The derivative of tangent, if I were to cover that up, what's left? So secant squared. Okay. What is the derivative of secant? Tangent secant. Or secant tangent. Yes.
This is much easier than memorizing the Santa Claus stuff.
Okay, great. So the table, this like triangle thing makes sense, right? Because even if I were to cover up the other secant, it doesn't really matter. What is still the derivative? Secant tangent or tangent secant. That multiplication can go in any order. Does that make sense? Okay, great. On to the third one. Cotangent. The derivative of cotangent is negative cosecant squared. The derivative of cosecant is negative cosecant cotangent. So guess what we're going to draw for this? A cute little triangle again, but this time it's a negative cute triangle. We're going to put cotangent at the top and cosecants on the sides. Now, following the same idea, for any of these, we can use the triangle to figure out what the derivative is. What is the derivative of cotangent? Negative cosecant squared. Okay. What is the derivative of cosecant? Negative cosecant cotangent. Or backwards, negative cotangent cosecant. Multiplication can go in any order. Yes? So it works the same way. The cos are just negative. So your triangle is a negative when it comes to the cos. Does that make sense? Okay, those are just tools to help you memorize it. Obviously, if you have a formula chart and you're allowed to use it, you read it off the formula chart. But all the other derivative rules we've had and we have apply. So when we start to differentiate, which is the verb version of find the derivative, we're just going to add these tools to our arsenal. If we find the derivative of y equal to tangent x minus cotangent x, remember, we can separate things by plus and minus signs, so we can do these two things separately. What's the notation I use to show I'm differentiating? Oh, this one's not prime because this is a y. dy over dx says I'm taking the derivative of y with respect to x. Okay. What is the derivative of tangent? Secant squared of x. What is the derivative of cotangent? Negative cosecant squared. But if it's already negative, what's negative negative? Positive cosecant squared. Voila, you just took your first derivative of a trig function.
For an upcoming quiz, we have to write dy over dx.
Correct.
Oh, we do?
That's the correct notation when it's in y equals
So
form.
we have to put that in our answers.
Yes.
Okay, just making sure.
Uh-huh.
It's not just y prime.
We will get to when it's y prime, but not yet. Are we okay? Can we try the next one? Maybe. Okay. We're taking the derivative of y equal to 4 secant x. So we start off with the correct notation, which is dy over dx equal to, okay, we have a constant in the front. Technically, by the constant multiple rule, that means we can kind of put it in the answer and then take the derivative of the function. What's the derivative of secant x? Secant x tangent x. So the derivative of 4 secant x is 4 secant x tangent x. Yes? Okay, we want to take the derivative of f of x equal to sine of x minus cosine of x. What's the notation I use this time? F prime, yes. When it's in function notation, that's when we use the primes. Okay, we do piece by piece. What's the derivative of sine? What's the derivative of negative cosine? Sine. Haha, Santa Claus, negative Santa Claus. We get it. Yes?
I hope.
Okay. Now, of course, it's not just that simple. You know it's never that simple. If we are going to take the derivative of this, you should maybe think to yourself, wait a second. Every single time we did derivatives before, we moved the x to the numerator so I could do power rule. I want you to kind of think like that again, except we're not going to use the power rule to move secant to the numerator. What can we use to move secant to the numerator? That's maybe on your formula chart.
The thing. What's it called?
Starts with an R.
Reciprocal theorem.
The reciprocal identity. What is the reciprocal of secant? Cosine. So I could rewrite this as negative 4 cosine of x minus pi. Notice I did not write prime because did I take a derivative yet?
No.
No, I just rewrote the h of x function. Now that it's in the numerator, and I have no denominators because I haven't taught you, it's called quotient rule. We'll get there. We haven't learned quotient rule yet, where we do stuff in the denominators. This I can take the derivative of with the rules and tools that I have. So we take h prime of x. This is negative 4 that we can hang out in the front. What's the derivative of cosine? Negative sine. What's the derivative of negative pi? 0. Now, we wouldn't really leave our answer like that because it's not simplified, and you could possibly do this in one step once you get good at it, but since this is our notes, I wanted to show this step. What would I do to clean this up, do you think? Yeah, what's negative 4 times negative sine?
Positive.
Positive 4 sine of x, yeah. That's a nice little cleanup step right there.
hard steps?
That's easy enough. You could probably do that in your head. I'm okay with that, as long as you tell me notation-wise what you're doing. But if you need to show the step, show the step. How do we feel so far? I want you guys to try E. What? You can do it. Every single term of a function you do separately. So when you're doing the first term here, what are you going to do before you take the derivative? Okay, cool. Put the x to the top, then you can take the derivative with the derivative rules we've had. Try it. Your brain will think of something to do. Give it a shot. Okay, I wrote it out in case you're stuck, but don't look until you finished.
Oh, the negative. Okay.
Yeah, so the question was, where did the -2 come from? When I do the power rule, I got to multiply this -2 to the front, then subtract 1. So the power rule, we still have to remember, because that's a tool in our tool belt to taking derivatives. We're just adding stuff on every time. Speaking of tools in our tool belt, if we look at letter F, which we will do together, what tools from our tool belt are we going to need to remember to use? The power rule and how to rewrite the square root. So let's do that together. How do we rewrite cube root of x to the 5th into a exponent power? It is x to the 5/3. Numerator comes from behind, denominator comes from front. Notice I did not put dy over dx because we are not taking the derivative yet. Minus sign is fine. But what should I change that third term to? 5x to the -7. The power when it comes up becomes negative. And secant of x is fine as well, because it's in the numerator. We can take its derivative. But every single piece we can do separately, which makes taking derivatives a lot easier. For the first one, we're going to multiply the 5/3 to the front and then subtract 1 from 5/3. Which means we are subtracting 3/3. What is 5/3 minus 3/3? 2/3. What's the derivative of negative sign? Negative cosine. The derivative of 5x to the -7 would be -35x to the -8. And then what is the derivative of secant x? Secant tangent, or tangent secant. That order doesn't particularly matter because it's multiplication. It can go in any order. Now, of course, if you leave it like this, I give you half credit today, but next time I will be counting it wrong because, oh shoot, 2 things. What did I do wrong? For sure wrong next time. Actually, I'm pretty sure I counted that part wrong today. What else will be wrong next time? Yeah, the cleanup step, right? Okay, yeah, we got to clean this up.
With the negative x to the bottom? No.
The negative x, this one right here,
Yeah.
will go to the bottom. What else do I need to clean up? This one, right? Okay. Now, is that a negative fraction? So does it go to the denominator? No, it stays in the numerator. So we're going to have 5 cube root of x squared over 3, which you could write as 5/3 times the cube root of x squared. It's the same thing. Minus cosine of x minus 35 over x to the 8th plus secant x tangent x. So now these trig rules just become part of the things that we know how to do for derivatives. I can't believe I forgot my dy over dx. It's embarrassing. I made such a big stink out of that.
But you forgot it again.
Well, once I write it once, I'm saying this is equal to this.
So we can do that in test?
Yes, as long as you've shown me once that you have taken the derivative, I don't care, but you may have a teacher and or maybe with AP standards, if you're taking AP, it might require you to. So it just depends on your teachers, what they care about. Once you've said it once, you can just continue to do equals for me. Okay, let's apply this to writing equations of lines. In example 2, it says to find the equation of the line tangent to the graph of y equals x plus cosine of x at the point 0, 1. So if we're finding an equation, this is when we're going to want to do point slope form, which means I need to find a what and a what? A point and a slope. How do we find the coordinate point? We plug it in, right? So we have this formula y equal to 0 plus cosine of 0. Okay, I think few of us still have our formula charts out. What is the cosine of 0? It should be like a number. Cosine of 0 is 1. So 0 plus 1 is 1. So what is my coordinate point here? 0, 1. Fabulous. There's my point. I need my slope. How do we find the slope? Find the derivative and then do what? Plug in the number. Cool. So we're taking dy over dx, which is equal to the derivative of x. What is that? We're taking the derivative of this function, by the way. What's the derivative of x? 1. What's the derivative of cosine? Negative sine. Huh? That's Santa Claus, negative Santa Claus. You're thinking about the Pythagorean identities. It would have to be squared to be one of those. Those are still very well an option that could show up for you. Don't forget about your Pythagorean identities. Don't forget about them. Now we found the derivative. What are we going to plug in here? What number? 0. When we plug in 0, this is 1 minus sine of 0. What's the sine of 0? Oh, wait, sine of 0 is? Oh gosh, get your formula charts out, guys. What is the sine of 0? 0. Oh, I didn't hear you. I'm sorry. What is 1 minus 0? 1. Okay, so my slope is 1. So when we write my final answer here, we would do y minus y1 equal to m times x minus x1. Now, obviously, a lot of that's kind of boring. Do I need to do x minus 0? No, kind of boring. So then we have 1 times x. Do I need to show the 1? No, technically, if this were on an answer key, I would probably have it say this. But do we see where we got that from? Okay. Yeah, you can definitely still write it as y minus 1 equal to 1 times x minus 0. I'm just pretty sure on answer keys I've simplified it when it's multiplied by 0 because it's boring. Does that part make sense? Okay. Last example for today. It says determine the points at which the horizontal tangents occur on the graph of y equal to 2 cosecant of x plus 3 for the interval from 0 to 2 pi. Oof, a lot of vocabulary. We need to remember what that means. A horizontal tangent. A tangent line is that equation we've been finding when we do like the problem right above it, where we find a point, we find a derivative, and we write the equation. But if we think back to Algebra 1, what does it mean for a line to be horizontal? What kind of slope does it have if it's horizontal? Oh dear, this is a horizontal line. It's a Hoy line. What kind of slopes do Hoy lines have? 0. So we need to know where the slope is equal to 0 so we can find those coordinate points. So this is a little bit different than the other problems. We want to know at what x values the slope is 0. We want to know at which values the derivative is 0. So the first thing we're going to do on this problem is we're going to find the derivative. And again, I'm just numbering this because these are notes. You don't have to like number it when you do this problem, but that's not how you spell that word. Why does that look weird? Is that how you spell derivative? There's A right there. There we go. Okay, so we find the derivative of this function. The regular function is y equal to 2 cosecant of x plus 3. What's the derivative of that? I can't show both at the same time. I have to zoom out too big. So the formula is at the end of your problem right there. What's the derivative of 2 cosecant of x? Okay, I'll write it like just like you said it because that's great. 2 negative cosecant x cotangent of x. What's the derivative of 3? 0. So if I were to clean this up just because I don't love that that negative is inside that parentheses, this would just be negative 2 cosecant of x cotangent of x. I'm assuming that most of y'all will choose to do that in one step, and I'm okay with that. Bless you. So we have this equation for the derivative. Based on finding out the points of the horizontal tangents, all we want to do is solve the equation when we take the derivative and set it equal to 0 because of this horizontal tangent. So what I'm doing here, find solution to derivative equal to 0. We're trying to find the solution for when the derivative slope is 0. So we got to think back to when we solved trig functions. When we solved trig functions, what we wanted them to be was in 2 factors. And essentially this is in 2 factors. I'm going to add some parentheses here just to kind of split it in 2. Do we see that there are 2 factors? So we're trying to solve the equation negative 2 cosecant of x equal to 0 and cotangent of x equal to 0. I'm going to have you look through your formula chart for a second. Look at the back for where the shapes of all of the trig functions are, and look at the shape of cosecant. What can you tell me about the shape of cosecant? What does it kind of look like? Like an upward parabola and a downward parabola, right? It's the one that kind of looks like this. Right? Something like this. So will this ever be equal to 0? No. So this one, we have no solution. That's nice. Cotangent will cross the x-axis. So we need to figure out where it's going to be equal to 0. I want to let you think about this for a second. Where between 0 and 2 pi would cotangent be equal to 0? So if we look at our formula chart, for all of the places where tangent is undefined, the reciprocal of undefined is 0. So on your table, where are the places where tangent is undefined? Pi over 2. And what else? 3 pi over 2. That is the solution to where cotangent of x is equal to 0. Now this problem's hard because we're using the reciprocals, cosecant and cotangent. This could have been sine and cosine, and you would have read it right off of your graph the way we solved like the problems in the escape room right there. A lot of us just read it straight off our formula chart. That's what we're doing. It's just harder because they're reciprocals, so they're not on there. Once we've found these 2 places, the solutions, I'll highlight it in green so we know that's the answer to this. The question itself says, determine the points. We have x values. How do we find y values to finish out a coordinate point? Plug it into what? The derivative or the original? The original. So I'm going to take the original equation and I'm going to plug in pi over 2 and 3 pi over 2. For notation, just for our notes, the way you would write this is y of pi over 2. We don't normally write this in function notation like that, but this is to help us remember we're plugging pi over 2 into the function. This would be 2 cosecant of pi over 2 plus 3. What is cosecant the reciprocal of? Sine. What is sine of pi over 2? Guys, look at the table. What is the sine of pi over 2? So we have that the sine of pi over 2 is 1. What's the reciprocal of 1? Oh, we're overthinking that. What's the reciprocal of 1? It's still 1. 1 over 1 flipped over is still 1 over 1. 2 times 1 plus 3 is 5. The first coordinate point where we have a horizontal tangent is pi over 2, comma 5. So how would we do the second one? What number are we plugging into y this time? 3 pi over 2. This is 2 times the cosecant of 3 pi over 2 plus 3. Cosecant is the reciprocal of sine, so we can read the table for sine and just flip the number over. What is the cosecant of 3 pi over 2? What is the sine of 3 pi over 2? What's the reciprocal of negative 1? Negative 1. So this is 2 times negative 1 plus 3. And what is 2 times negative 1 plus 3? I think somebody said it by 1. Okay. So the coordinate point for this one is 3 pi over 2, comma 1. Oof. Okay, I know that last problem was a doozy because it's using some crazy vocabulary with horizontal tangents, but remember horizontal lines have a slope of 0. We know tangent lines are the derivative at a particular point.